right, this particular, you think about solving logarithms and solving equations with logarithms, and hopefully you remember back from Algebra 2, if something has logarithms in it, we condense it so we can snapshot. That's what we always want to do with logarithms if we can. But one of the things we try with unknown bases is trying to get the bases to be the same so that we can just use equality, properties of equality to solve. So equation solving and modeling is what we're going to go after. We probably won't get to the word problemy stuff, the modeling stuff until tomorrow, next day. So review solving exponential equations algebraically and graphically. Lots of algebra today that we're going to use. And you're going to find out it definitely is a step above what we expected people to do in Algebra 2, using those logarithms. So reviewing solving logarithmic equations algebraically and graphically, applying Newton's law of cooling tomorrow or the next day, and then some extension topics, using some things a little bit differently than you have in the past, because we do have Newton's law of cooling in your Algebra 2 curriculum, but it's kind of a just stick the numbers in and everything works out beautiful thing. And we don't want to do that. We want to do the ones that are a little step more difficult than that. And then apply regression models related by logarithmic re-expression. Now that's an interesting topic, and that one, again, tomorrow or the next day, depending on how far we get. So 3.5 is equation solving and modeling. And for any exponential function, remember that if we can get the same base, then in order to have the property of equality, then the powers would have to be the same. And then we've got b to the u equals b to the v. The only way that's going to happen is if u equals v. And that's one of the first ways that we go to solve when we have bases with unknown powers. And then for any logarithmic function, if logarithm base b of u equals the logarithm base b of v, since they both have the same logarithm with the same base, u is going to have to equal v. That's the way that that's going to work. So equality is just basically logic. You know, if we're saying that things are going to be equal to each other, they have to be perfectly equal to each other. That's what has to happen. So methods, if we can, we're going to get common bases, and then B, take the logarithm of both sides and expand, and that's going to be something you probably didn't do a whole lot of in Algebra 2. Use factoring and solving quadratics techniques. I'm going to get a little interesting towards the end of what we do today. So example 1 says solve the exponential equations algebraically, and the method that we want to use here is getting common bases. So when we look at A, we want to focus on those bases and think, okay, 9 and 27. Is there some number that I could raise to a power that could give me both of those? Yeah, it'd be 3. So 9 is 3 squared, and we would still have to raise that to the 2x power. And 27 is 3 cubed, and we would still have to raise that to the x minus 1 power. And then we have to remember that when you raise a power to a power, you're supposed to multiply those exponents. So this would be 3 to the 4x equals 3 to the 3x minus 3. And like I said, here's where we use our logic and say, wait a minute, the 3's as bases are already the same. If they're already equal, I don't really need those anymore. I'm going to need 4x to equal 3x minus 3. That's the only way this is going to come out equal. So we'd subtract 3x from both sides and get x equals negative 3. And as always, getting a negative in anything that involves powers or logarithms, you know, it's one of those things where you need to check and see, hey, is this really going to work? So we certainly could throw the negative 3 back up here and say, well, that would be 9 to the negative 6, and this would be 27 to the negative 4, and make sure that those are going to work. Most of the time, the fear comes when you're doing logarithms and you get a negative answer, because usually we're not going to be able to evaluate that negative. Then for B. B looks complicated. So one way to uncomplicate it is to say, I've already got a fraction over here. I'm going to go ahead and divide both sides by 20 and see what I really have. And then start thinking, okay, 1/2. 1/2 squared, bless you, 1/2 squared is 1/4. So if I leave this base of 1/2 right here, and I write this as 1/2 squared, now I have the same base again.
Raise that 1/2 to
Oh, that's supposed to be the x over 3. I suppose that's really tough to make out, this little piece right here. There we go. So that should be the x over 3. And then we look at this and say, well, they already have the base of 1/2, so I'm going to go ahead and say x over 3 has to equal 2, and multiply both sides by 3, and get x equals 6. Now, there was another way to do this problem, and that would be instead of using 1/2, use 2 as your base. We definitely could have done that. We would have had some negative exponents to deal with, but that's another way to do this problem. So now, look at that one. Wow, nope. Yeah. This one says we're going to use a base of 2. So the first thing I do, if that hint isn't there, is I go through this and I think, okay, numbers to pay attention to: 4, 16, 8, and 2. And just kind of work through it in your brain. Oh yeah, those are all powers of 2. So now what they're getting at is we're going to write all this stuff as powers of 2. So how do you write 1/4 as a power of 2? 2 to the now it's got the cubed root of negative 16, and then that's raised to a power. But I want to focus our energy on this for a second. 16, 2 to what power? 2 to the 4th. What's a cube root do as a power? 1/3. So that's going to be a little awkward because that'll be 2 to the 4/3 power. But it's okay. We'll deal with that. All to the x plus 4 equals 5th root of 8. Again, I'll do goodness, who can remember this? 8 is 2 to the 3rd. And now we, of course, remember, yeah, the index is always the denominator. So 2 to the 3/5. That's kind of unreadable there. 2 to the 1st. We'll put the little 1 there, even though normally we wouldn't do that. And then we have the 2x minus 1. All right, so now I see one thing we can deal with right away, and that is a set of parentheses that are actually doing something. There is some simplifying we can do with these. Division. How do we do division with similar bases? We subtract. So I'm going to leave this little bugger over here all alone for a minute. But realize that over here, I'd have to subtract 3/5, and 1 is the same thing as 5/5. So 3/5 minus 5/5 would be a negative 2/5. Trying to write those always big enough here, so we can see that. Now, we have powers being raised to powers. To simplify those, we need to multiply. So a little 2 to the negative 2, I'll leave sit here for a little bit longer. But now I need to distribute that 4/3 for the x plus 4. So that'll be 2 to the 4/3 x plus 16/3. Because remember, this 4 is like a 4 over 1. Top times top, bottom times bottom of fractions. Over on the other side, we'll have 2 to the negative 4/5. Again, think of that 2 as 2 over 1 plus, oops, forgot the x, x plus 2/5. Now we're closing it up. We got another 2 on the left-hand side that we can simplify. They have the same bases. Now that we've distributed that power, now we can go ahead and multiply these two bases of 2 together. What do you do when you multiply similar bases? add the exponents. Well, this is a -2, and notice we have thirds back here. So that would be like a -6/3. So we're going to get 2 to the 4/3 x. Can't do anything about that. There's no like term for that. But then we have -6/3 plus 16/3, which is 10/3.
Where did the -6/3 come from?
This was a -2.
Oh,
So to get a common denominator, we'll do that over 3. Bless you. So far, so good? Just a lot of algebra, right? Okay, now, what do you think we can do? Drop the big 2's. We don't need these bases anymore. They're already equal to each other. That is not the problem. This is the problem. The powers have to be equal. The 2's are already the same. I mean, that's why we did this problem this way. The 2's were already the same. And then it's up to you whether or not you want to work with fractions all the way through this or not. Fractions or not. Okay, then let's multiply by the LCD. What's the LCD of everything? Multiply by 15. Well, here, the 3 and the 5, 3 and 15 will reduce to give us a 5. 5 times 4 is 20x. Same thing here, 3 and a 5, 3 and a 15, 5 times, I keep giving the answer instead of explaining that. 5 times 10 is 50. Over here, we would get a 3 because 5 and 15 and divide and give us a 3, so that would be -12x. Same thing, we still have a 5 in our denominator there. That's going to be a 6.
So when you were dividing out 6x plus 4 top, how did you get 10/3?
Because this is an x term. We cannot add that with anything else up here, but -2 is -6/3. And that needs to be added with a like term over there, which is the 16/3. So -6/3 plus 16/3, that will give us the 10/3.
What did you multiply to get to 16/3?
16/3, 4/3, backing up a step here, times 4. Top times top, bottom times bottom. So this would be 4 over 1. Okay.
And then I have one.
Yeah.
The 15, if you multiply that out, how did you get the
Remember, this is like a 15 over 1 times everything. So what we would do is reduce and say, okay, well, this time it's going to end up being a 5. 5 times 4 gives you the 20x. Here it's going to be a 5. 5 times 10 gives us 50. Here it's going to end up giving us a 3. -4 times 3 would be -12x. Here it's going to end up giving us a 3. So 2 times 3 would be 6. Anybody else? Anything that's going to stick it in your craw right now? All right, so let's add 12x to both sides. I'll put the steps in here. I don't want to lose anybody at this point. Subtract 50. Divide by 32. And realize they're both divisible by 4. Look at that, huh?
Wait, there were 2.
We have plus 12x to both sides.
Why didn't? Is it negative? How is it negative? Oh, that's why. Got it.
That's a monster there. Yeah, that's a monster. Look at all this.
Please no.
Maybe for fun. Look at that. That is beautiful. That's a lot of algebra manipulation there. That is good stuff. All right, no, they're not good. Your homework even, I don't think gets to that level. But you need to be able to do those manipulations as you go through this stuff. Remember, in calculus, there are going to be times when you can't use exactly what's sitting in front of you, and you have to manipulate it in order to use it. So this one says, now we've got trouble. Solve the exponential equations algebraically. And the method we want to use is take the logarithm both sides and expand, because 3 to the something is 11. Really can't get those bases to match. So what we're going to do is we're going to get you used to using natural logarithm more, because for calculus that's going to be really helpful for you. So we're going to take the natural log of both sides. And then if you look at that, go, now what? Well, we do the one thing we can do, which is say, hey, this is a power. Powers are supposed to become multiplication. So now if we want x, we're going to go ahead and divide both sides by the natural log of 3. That'll give us our answer. So just manipulation using that natural logarithm. Again, natural log e come in pretty handy in calculus, so you gotta make sure you can do those things. Natural log of 11 divided by natural log of 3. And 4 decimal places for logarithms, so 2.1827 for that. So different than what we've done in the past, which would be, hey, let's just take the logarithm base 3 of both sides right away. But you know what? When we do that, we end up using the change of base formula exactly like the said one. So it doesn't make any difference. All right, taking a look at E. Can't take natural log right away. You can only take natural log if there's an E all exposed and ready for me. That's not all exposed and ready for me. Gotta get rid of that 9. So 30 divided by 9 gives me 10/3. Now the E is exposed. Now I can take the natural log of both sides. This will drop out because it's an inverse. I'll find whatever the natural log of 10/3 is, and then divide it by 2. And again, wait until the end, do it all as one punch in, don't start writing intermediate steps down, show the algebra to get them, but we want to keep this exact all the way through. So there's our natural log of 10/3, and divided by 2, so 0.6020. With our rounding to 4 places. F. What should we do? No crying aloud. Remember, math is, we never give up and there's no crying. Natural log. Let's natural log both sides.
No. Scroll.
Can't get the bases to be the same. Can't. Oh, sure. Higher. Think about what we just did in the last problem that was like a little step easier. What did we do?
Oh, got rid of the number in front of the E.
Looking at this one. Bring the x minus 5 out in front. Let's see what we're doing. And the 3x plus 4. Oy. We need x on one side, and we need just numbers we can punch in on the other side. In order for us to do that, we're going to have to distribute this natural log of 7 through these parentheses. And we're going to have to distribute this natural log of 2 through these parentheses, because we can't move the x's over on the other side until we can get them together. So we'll have x natural log of 7 minus 5 natural log of 7 equals 3x natural log of 2 plus 4 natural log of 2. Oh my. Lions and tigers and bears. What? Oh my. So now, let's get the x's on one side, and let's get the stuff that's just numbers that we can punch into the calculator on the other side. So I think I'm going to subtract the x natural log of 7. There. They're not like terms. And then I'll go ahead and subtract the 4 natural log of 2 from the other side. Let's see if I can squish all this in. Does everybody see that the left-hand side is now just a number? If we punched it in, we could get all of that, right? Okay. So what we have to do is try and separate the x out of all of this gunk so we can divide and get our answer. If we can distribute it, do you suppose we can factor it? Let's work forwards and backwards. Let's pull an x out. Bless you. Now, since it's multiplication, we can divide. Now, that's going to give us our answer. If you're thinking, okay, should I put all of this back together? Like, should I say 7 to the negative 5 power, put this negative 4 back up? I wouldn't. At this point, I'd just make sure I put parentheses on the top and parentheses on the bottom and punched it all in. Make sure that it works. Find our x value. We've done all the algebra we need to do. Should be set. There it is. Negative 93.6270. Again, negative answers make me a little squirmish, so I probably would go back, put back in there and make sure it works. But it does. It does work. It's just really lovely. It's really lovely. So now I know I'm going to need more room. This one. Woofda, as Sven and Emily would say. So now what? Well, we better try and get at least one base exposed, so it's either divide by the 3 or divide by the 4. We have to. Gotta get something myself. I think I'm going to divide by the 3. I'm going to make that x plus 1. I don't like the 1 plus x. It doesn't matter. It's commutative. It doesn't matter. Oh, all right. natural log.
Would you have to divide the 6 by the 3 too? You just
We don't, because technically this wasn't multiplied together yet. One is a power and one is not. And so the multiplication is dealing with just the front portion. Because once we figure out what this is, we still would need order of operations. We'd have to do this part first. So we just hang on to that 4/3 and say, okay, what's next? Well, natural log would be next. That's what we're gonna have to do.
Would it still be a 6 or would it be a 2?
Oh, that's what we were just talking about, Emmy.
well, yeah.
Because this has a power, remember, this has to be done before we could do any multiplying out in front. So we just hang on to it. Oh, doesn't that look nummy?
Wrong. Wrong.
Well, we better figure out what to do over there on that right-hand side, because things are getting a little scary. Multiplication in logarithm language means what? Addition. Finally, we can separate those a little bit. Multiplication in logarithm language is addition. Think about what we've done today and where we're going to need to go with this. So what should we do next? Bring those powers out in front for multiplying. Then what?
Oh no, I'm multiplying.
Distribute it. Whew. What will we do next? That's the last problem.
Trying to move the stuff to the other side.
X is on one side, anything that we could calculate with the calculator on the other side. So we'll have 2x natural log of 5 minus x natural log of 6. On the other side, we will add that natural log of 5. Now what? Get an X out of there. Close.
And then just divide the 2 on.
There's a monster to punch in, huh? So let's see what we can do with this. Parentheses. Natural log of 5 parentheses plus natural log 4 divided by 3 parentheses plus natural log of 6 parentheses parentheses. The divided by parentheses 2 natural log 5 parentheses minus natural log 6 parentheses parentheses. Phew. Natural log 5 plus natural log 4/3 plus natural log of 6. Finish it off. There's our wonderful answer. 2.5848. And thank goodness we're switching to another method, which means it doesn't get harder than that. That's as difficult as it gets. A lot to keep track of. Again, it's the tortoise and the hare. Be the tortoise. Slow and go through it all. Now, things get interesting. Use factoring and solving quadratics techniques. With that, think proportion. Cross multiply. Just gonna skip a step. I'm not skipping anything. Need to distribute the 5. Use factoring, solving quadratics techniques. Well, then that would mean we're going to need a 0 on one side, because when we factor and find the zeros, that's what we're doing. So we'd start this way. We'd say, hey, let's do this. Let's subtract one of these e to the x's things off of here. Let's see what we have. 4e to the x minus 5. Wait a minute, I'm not necessarily going to need factoring to do this one. I could move the 5 over to the other side. Because they said it could be solving. I'd divide by 4. Now what? Oh, yeah. Seems way too easy compared to what we just did, but remember, we were truly building up those manipulation skills there. So we could punch in natural log of 5/4 and 0.2231. We could have expanded this out and said natural log of 5 minus natural log of 4. You're going to get the same answer, just following those properties of logarithms. So, factoring, solving quadratics techniques. Oh my goodness. Look at I. Well, since having it on both sides doesn't seem to be helping a whole lot, maybe I'll move everything over to one side. And it looks like this is the squared term here. So let's see, if I move this over by subtracting, I'll have this. Oh, you'll lose your zeros. Remember, the number of zeros we have is determined by the degree. So we can't divide it out, or we're going to lose our zeros. It's like if, let's see, what was another one what was very common for people to lose zeros. This. We move the 27, move the 27 over, take the cube root, and we get an answer of 3. But how many solutions is this supposed to have? 3, and we've only found 1. We lose it if we do that. So don't divide that out. Factoring it out, yes, because that'll keep it intact. But you can't divide it out. So now, I'm guessing you'd say, well, let's factor it. well, both of them have an e to the x, and they both have an x. That makes for some interesting factoring. Take out the x and the e to the x. Wherever there's an x, there's a solution. So, if this x is 0, then the whole thing would be 0. If e to the x equals 0, this whole thing will be 0. Wait a minute. Can you raise e to some power and make it be 0? Yeah, the first is e. Yep.
On the very first line that you wrote,
This piece? This is just subtracting this from both sides.
oh,
Getting it over to 1. It is undefined. This one is not going to give us an answer. This is undefined. How about that set of parentheses there? What's the 0 for x minus 3? 3. How many solutions was it supposed to have? Just 2. It was x squared. So we found them. It took some serious manipulation, but we found them. Some good factoring. Alrighty. What is this G? Oh, we already did G. This was in case I couldn't fit it on the other page. I already did that one. Alright, now, solve the exponential equations algebraically. Cool. Use factoring, solving quadratics techniques. So same directions as we had before. And now I notice things are getting weird. What is up with that? What's a negative do? Reciprocals? Oh man. Can't solve for something that's in the denominator. We're going to have to multiply everything by e to the x. Won't that be fun? So here it would cancel out and we get a nice little 3. But here we're going to have e to the x times negative e to the x. Let's see. The bases are the same, so that means we're supposed to add the exponents. X plus x, 2x. And over here, 2e to the x. Now they said to factor, solve, as you would quadratics. And that's the first thing we always try with quadratics anyway. So I start thinking, well, which one's my squared? Which one's my to the first, and which one's my constant? Well, I think the constant's a dead giveaway, which is the only one that could possibly be our squared term. This has to be it. So what we'll do is we'll subtract 3 and add e to the 2x to both sides. And we'll see what we have.
Why did you write it different ways? You put -3 to it's the same thing.
I am just showing the subtracting the 3 and the adding the e to the 2x over the other side. Because I mean, right now I want to play it safe and not lose anybody on any steps. So some of these steps you're going, oh my gosh, I can't believe she's writing that down. But I don't want to lose anybody. Now, what is it that's bothering you about this problem? What is it that if it weren't there, you're thinking, I could do this? The e to the x? Well, then let's do this. Let's substitute for it. Let's get out of there. Let's substitute for it. Let's see what happens. Let's say e to the x is w. Now remember, we're going to have to substitute that back in when we try to get our answers. But for now, I think this will make this something you'll look at it and go, oh, I can do that. Do you know how to factor something that looks like that? Of course you do. Two numbers that multiply to -3 and add to 2. Plus 3 and -1. So here's what we're saying. W plus 3 could be equal to 0. Or W minus 1 could be equal to 0. Now why am I bothering to write that out? Because we substituted in for W. Remember, we're not done yet. So I'd subtract the 3, add the 1, and then remember, wait a minute, it wasn't W in the problem, it was e to the x. We're going to be able to raise e to some power and magically get negative 3. This is undefined, this is ignored. Can you raise e to some power and get 1?
Yeah.
There it is. Got it? So if the e to the x is the part that drives you bonkers, substitute for it. Get rid of it. Which brings us to one that's a little more involved. Step 1. Can we hang on to that for a second? Yeah, let's cross multiply. Now, I mean, this would be a great time for what you just said. Even what we did in the last problem, what should we do next? E to the x, everything here. Put them all over. There's something to do at this point. Cassie, you said something, but I couldn't hear you. Quadratic formula? Yep. Everybody want to work with E right now or later? Later? Let's substitute then. Because the hope would be that it's factorable, but there's not two numbers that are multiplied to -1 and add the -10. And I do think this one goes a little quicker with completing the square. So either way, you could do that. But I think I'm going to do completing the square. So I've got a -10 for my middle term. My a value is 1. -10 divided by 2 is -5. And when I square it, I get 25. So this would give me w minus 5, the quantity squared equals 26. Square root w minus 5 equals plus or minus the square root of 26. Add 5. I realize I'm not done, but I'm close. Because w equals that, we're saying e to the x might equal, well, I guess we're stopping here. We're almost done. We'll finish that one up tomorrow and then keep going. And yeah, the homework is a lot easier than what we did for notes today. But there it is, page 300, 1 through 6. Let me put the lights up if you need to. 11 through 16. And 29 and 34. And I will have to save that. So just roll it like that. Right. Boy, lots of really, really good algebra manipulation today. Thanks for hanging in there, everybody. That's a lot of material.